proiettore non funziona. Okay, so there is one person in class, and there is a problem with the projection here. So I need to go 1 second to find somebody who can help us. Just a second, I'll be back. Okay, we are back. So by now you should have uh, seen what is the Slido code for asking questions, given I've been sharing this window for a while now. Uh, so before switching to the actual lesson, let me say that I have uploaded on Classroom another Python notebook. And I mean, I'll not go into the details of the code. I'll just be, uh, um, can you guys hear me? I mean, this is what you said before. It was working. I don't know what, yeah. Okay, so Hermano, you probably have some problem. Anyway, so as I was mentioning, I have uploaded a Python notebook where I have formalized a simple grid word um, in the form of a macro decision process. So I have created a class for transitions where I collect my transitions. I have created the dynamics of the um, MDP, and I have given you one example of what means to take an action in here, what the reward that you get, um, the termination condition, and the actions that are available to the agent. And finally, I have run one example of value iteration. So I've created one code that runs for you value iteration. So if you want to look at it more in detail, you can do it at home, and then I mean, you are at home, most of you. You can do it in non-class times. And yeah, if you have questions, let me know. I'll not spend a lot of time on this now. We can come back to this. If you have questions, probably in the next class at this point, you can ask questions on Slido regarding this too, if you have doubts. But let's go to the actual topic of today. And again, before doing this, I want to recap what we have seen in the last two classes. So we have introduced the formalism of Markov decision processes as a representation to describe problems where we have an agent that interacts with an environment and receives some signal, which is a reward. And the goal of the agent is that of maximizing the accumulation of these rewards over time. Um, so we have said that solving a Markov decision process means um, finding a policy that can be optimal if it maximizes the true value function, where the value function is again the expectation of um, the cumulative reward that an agent can get from a certain state by following a certain policy. Okay? Then we have said, if we know the transition function, using a value function, we can use value iteration and policy iteration to find the optimal actions and the optimal value function that would allow an agent to achieve the goal that it has to achieve, so complete the task that it's assigned to him. Then we say the problem is that in most cases, in the real world, we don't know the transition function, which is why we want to do learning, and specifically we apply reinforcement learning. So we have seen one simple example of reinforcement learning in a very simplified case, which is the bandit case, where you have one simple single state and a set of actions, and the agent has to choose among these actions, although there is no change in the state except the only thing that the agent sees is not a change in the state, but a reward signal. This reward signal is what the agent is trying to maximize in expectation, because there is, again, given that there is no trajectory, there is no next state, so we don't have a sum of rewards. The sum of the rewards corresponds just to the reward that you get in that single state, in this case. The agent wants to maximize the mean reward. So in expectation, that's how we compute our value function, and we have seen a couple of examples to do that in the case of stochastic environments where the reward was stationary and non-stationary as well. And yeah, so we have seen a bunch of methods for doing that, and we have seen also a policy gradient method where we have seen instead of computing a value function, we directly compute a policy. Okay. Now we'll introduce something which is slightly more complex in the sense that we are now bringing back the notion of sequence. So our agent, by interacting with this environment, will generate trajectories of states, action, rewards, and termination conditions. And by looking at the returns that we have said to be the sum of the rewards that the agent gets from a certain state to the end of the episode, so this is the return. By looking at these returns, the agent will try to find a policy. Okay, so let's look at our material more in detail. We have said already last time that differently from dynamic programming, which is the planning situation that we have in value iteration and policy iteration, we assume that we do not know the transition function. So we don't have a complete knowledge of the environment, which means we don't know also the reward function. This is all external to the algorithm, and it's just received as an input by the algorithm. And as every reinforcement learning algorithm, Monte Carlo methods require only experience, which means that there is a word outside from the algorithm, outside from the agent, the true model, let's call that, that generates transitions when an agent takes an action. So the agent is in a certain state, it performs an action, and it receives back, again, a new state, a reward, and a termination condition. Okay? Just to repeat again, what's the setting that we are in. And the agent does this several times until this termination flag becomes true. When this termination flag becomes true, then the environment gets reset. So when the reset happens, the agent will be like if nothing happened ever in the initial state. So there will be a reset, complete reset of the environment. The agent will be again the initial state, and it will try to repeat again what it did or change something or what it did. Okay. Okay, so again, the probability distribution of the transitions is unknown to the agent. This means that the agent doesn't know the transition function, doesn't know the reward function, doesn't know the termination function. So we said already for the planning situation that in order to compute a policy, we need either a policy that directly policy or a value function. And computing a value function means to compute in expectation what is the return. Now, what is a good way to do this? As we have seen for bandits, we have said for bandits, we just sample rewards and we average them. Now, we'll do the same thing now in the Monte Carlo setting, where we'll basically sample returns, complete returns. So the agent starts from the initial state, it will follow some policy, will generate a trajectory until a termination flag becomes true. This will allow us to compute the return for every state that the agent has traversed, right? And then everything will be restarted again. So let me give you a short example here by drawing something very bad because I don't have the pen here. But so let's say this is our 2 by 3 grid word, which is our MDP. Okay. So 2 by 3. So this is the initial state. I will write I here. And this is our terminal state. So the agent receives plus 100 here. I will only write plus, and you can remember this. So this is termination state. This is plus 100, and it receives minus 0.4 in every other state. This is one example of a grid word that we have already seen. Now, what happens? I can do two things. One is set the maximum number of steps that the agent can take, meaning I decide that if the agent doesn't reach a terminal state in 10 steps, then the 10th step becomes a terminal state for me. Okay? So, if, for example, if the agent is behaving randomly, it will wander around here, it will be wandering around here, and it will not be here at the 10th action, right? Actually, at the 10th state, right? The environment will be, maybe the agent will be here, the environment will be reset, and the agent will be again here. I can compute for this, I will collect one trajectory, right? This trajectory will be composed of my 10 states, my 9 actions, my 9 rewards, and my termination flags. From this trajectory, for every state that the agent has been visiting, I can compute a return, right? How do I compute a return for each of these states? I look at all the rewards that come after that state, right? So I forget what happens before, and I look at what happens after that state and sum the rewards that come after. So that's the return that you get from that state. Okay. So from here, I will sum all the 9 rewards that I got. From here, I will sum 8 rewards. From here, I will sum 7 rewards. Okay. Where here, 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 I'm assuming we have a new state. Okay. This is one situation when we said we reach the maximum number of steps. I can also set the maximum number of steps to infinity. Okay. So in that case, or when the agent reaches the termination state before the number of maximum steps, then the episode will terminate when the agent will be here. So for example, if the agent receives a termination flag true after 4 actions, then my trajectory will be composed of 5 states, 4 actions, 4 rewards, and that's it. Okay? So I will compute my return in this way. So in this way, I can compute my return 1, my return 2, my return 3 for every trajectory that the agent is generating from an initial state. So every time the reset occurs, I have a new trajectory, and this gives me some returns for every state that the agent has visited. And we can look at all of them, average them, and this will be our way of computing the value function in this case. So we'll see more in detail how to do this, but this is the overall idea. So as I've mentioned, as I've explained in this example, the experience is divided into episodes. All episodes have a termination condition eventually because either the agent will fall in a termination state or you force the termination by setting a maximum number of steps. And then when we complete one episode, we can estimate our value function. Why? Because when you complete an episode, you have the reset, so you have a new return that you can compute for every state that you visited, so you can update your value function. And then you can, after you update, you start again behaving, following your policy from that initial state. So one question that might arise is, why is this called the Monte Carlo method? It's a Monte Carlo method because, I mean, we have seen that Monte Carlo, this naming is used for all the processes that involve significant random components in sampling, right? Because by interacting with the environment, we are actually sampling trajectories, sorry, sampling returns out of the environment. Okay. Um, let's move forward. So I have given you already this explanation by stating a similarity with bandit methods. There are significant differences here in the fact that there are, in bandit methods, we have said that there are just single states. Here we have several states, more similar to contextual bandits. Now, there is also another difference, which is the major one, which is the fact that the states are interrelated one from another, because by taking an action from a certain state, I go in a new state, and this probability of falling in a new state depends on the previous state and the action that I have taken, right? So there is one other thing that this generates as a consequence, which is the fact that the return will be determined by every single action that the agent is taking, right? Because the fact that I fall in a certain state depends on the action, and I will be able to choose some actions from the new state, and maybe only from that state, because I've been going in that state, which means that my policy brought me there. Okay, so here there is a problem of, in general, what is called credit assignment. Credit assignment means what is, if, for example, if I compare two returns, what is the actual action that made me collect more return in this case? What is the real difference here? Maybe I changed more than one action, so I need to know what is that actually brought me something more. The other complexity here is that all the action selections in every state are under learning, which means that the problem is non-stationary here as well, right? Because you're trying to estimate something, like the return, based on something else, the policy, which is changing. So it's like something that is trying to reach something else, but this is moving, and this is trying to reach, and this is moving. So, given these premises, I want to say how we'll proceed from now on, in the sense that, like we did for when we introduced the notion of value functions, we'll first see an algorithm which is similar to value iteration, in the sense that we'll see something that will allow us to compute a state value function, right? What we call V. Huh? So this will give us an understanding of how to do that. And then we'll switch to something which is more similar to policy iteration, where we'll start with a policy, and then we will evaluate by using these methods that we'll see during the value iteration part, let's say. And after that, we'll see how to improve our policy. So very similar to policy iteration algorithm, just now we don't know the transition function. We'll need to understand how to estimate the value of a policy in a value iteration-like fashion, and then we'll compute an improvement on our policy. And again, we'll switch from using V to using Q, because we said last time, we don't know the transition function. So V, for us, if we want to take some action, and we don't know the transition function, is useless, because in order to see in which state we fall, in, we need to take an action, and we are done then. If we take an action, we take that action, we cannot come back unless we restart the environment. Okay. If there are questions on this, we'll look at the Slido webpage soon. So if you already have questions, start posting them. No, è andato su. Ok. Sorry. So we need now, as I was saying, a method to compute a state value function given a policy. So the policy is given. We want to evaluate our policy. What does it mean to evaluate our policy? It means to compute what is the value, so the expected returns that we can generate by following that policy. So this will be basically computing the expected cumulative future discounted rewards from any state S. So as we said, the obvious approach here is we just collect all the returns, we average them, and we obtain our estimate. But let's look at this more formally. So we want to estimate the value V pi. Why there is this pi dependency? Because we say the value depends on the policy, because the policy generates the trajectory. So the trajectories give us the way to compute the returns, and the returns are, as a consequence, depending on the policy. So given that the value function is the expected return, then the value depends, like the returns, on the policy. So we want to estimate the value of a certain policy, of a certain state, under the policy pi. And we do this by following our policy for a certain number of episodes and looking at those that pass through this state S. So every time the policy visits mean goes in state S, we will be able to update its value. Of course, in a single episode, S might be visited several times. So we'll also consider two different kinds of methods. One where we only look at the first visit to a certain state, and another one where we update the value for every visit in the same episode again to that state. Maybe a question that can arise: how is it possible that the agent visits the same state more than once? Very simple. If we go back to the previous example of the grid word, like the agent goes up and it goes back down because it's following a random policy, then that's the second visit to the initial state. We have a first visit Monte Carlo method and an every visit Monte Carlo method. In the first one, we estimate the V pi as an average of the returns that follow only the first visit to a certain state. This is what we will be focusing on, and it's also the most studied way of doing this. Although the every visit Monte Carlo method is actually also being used a lot nowadays, because it's very easy to be used in the case where you're using a function approximator, where you basically create a sort of data set where you map a state to a return, right? So if you want to cast this problem in the form of a machine learning problem supervised with a neural network, let's say, then you have your neural network that represents the V function. So it takes as an input the state, right? And you want it to output your value, then what can you do? You can create a data set where for every state, which will compose your data part, you can associate a label, which is the return that you computed. So in every episode, you compute all your returns, you create these, you set these as labels, you create the input to be the state, so you do the supervised training. In this way, you can use, for example, an L2 loss, so a mean square error loss, and this will be basically allowing you to create your value function using a neural network. Very simple. Okay. So here is some pseudocode for a first visit MC method. So again, what is the input of this algorithm is the policy, right? Because we want to evaluate our policy. So here the policy is given. We want to compute the value of this policy. How do we do it? Sorry. We initialize our value function randomly or uniformly to 0. So for example, if your value function is a neural network, right? If your value function is a neural network, you can initialize it with random weights, and that's fine. So that's the way you can do it. And I will be trying to contextualize this in the neural network cases, just because this is nowadays the standard that you will do. If you do reinforcement learning, you will do basically deep reinforcement learning and use some neural network for computing your value function policy and so on and so forth. So I will always try to contextualize things in this scenario, because not only you will have to do the project using neural networks, but also because it's relevant for any job that you might get in the field. Okay, so we create a buffer somewhere where we store all the returns that we collect, okay, for every state. So how do we do this? We create this buffer, it's initially empty, and then we start looping. Looping means that we start generating episodes, okay? By generating these episodes, we collect trajectories, and for every state visited by the agent during these trajectories, we compute our return. Actually, here we need to be careful. In this first visit MC method, we update the return, right, only if the state is visited for the first time. What does it mean? It means that it doesn't appear in any previous state. So if the state is not being checked already, then we compute the return for it. After we compute this return, we append this return to our buffer of returns. Basically, again, this is a mapping from every state to a return. So basically, this is what I was saying before. I'm creating a data set where I'm mapping states to returns. And then we are averaging all of them, okay? So I'm, keep in mind one thing. I'm never, ever here clearing my buffer, right? So I'm not clearing my buffer because I want to keep track of all the returns and I need to average them. So in order to average them, I cannot clear it because otherwise, I mean, I cannot do an average of averages because it's not the same thing. The average of the averages is not the average. Okay, so again, looking at the neural network case, this is the only thing that changes. This part here, B, S gets average of returns ST, where basically here you can apply your loss, where your loss will be, again, a mean square error on the data set. And the mean square error is actually computing an average for you, right? Is letting the function approximator estimate an average for you. Okay, so here are some useful information that, I mean, is relevant, uh, but I mean, you don't need to know this necessarily by mind. So you need to know that both MC versions, so first visit and every visit, both converge when the number of visits to a certain state goes to infinity, but that's just the standard thing, right? So for every sampling process, if you have an infinite amount of samples, then your estimate will be converging to the true value. This is nothing new. So for the for first visit method, every return will be an independent and identically distributed estimate of B, right? Of the value. The estimate has a finite variance, and the standard deviation of the error decreases with this magnitude, with n being the estimate. For the every visit case, instead, the estimate converges quadratically to the value, to the true value. So before moving forward with an example, I guess, I mean, this example actually is not very, I'll not be going into the detail of this as the description of the blackjack part. You can look at this at home. I will just show some plots. But before doing this, let's see if there are questions. No, this is not the right window. Questions on Slido, please. I'm opening the chat, but questions on Slido. So Slido code is 3924. What is A, R, and G? So let's start again from here. So this goes back to when we defined our Markov decision processes, right? A are the actions. So if you go to the MDP slides, right, we said a Markov decision process is characterized as S, A, R, so where S is the set of states that exist in the environment, A is the set of actions that are available to the agent, R is the reward function, and then we have a transition function, which is, again, like the reward function, is unknown to the agent. Okay? G is the return, we say this several times, which is just the sum of the rewards, in this case discounted by gamma, the discount factor, discounted by gamma, it's just the sum of the rewards that you get from every state. Okay, this should be covered. So everything seems so abstract. So, I mean, abstract in the sense that you, can you clarify what means abstract for you? Because I've been trying to contextualize this and give you examples of grid words to start, right? But this applies to any reinforcement learning problem. You can do this for your, I don't know, you have your robot that needs to navigate from here to there, and you can do the same thing. This is just an abstraction that I'm using to simplify things, but the same algorithms apply. And if you're talking about abstract in the sense that you don't know how to do things because it's just theory, this is why I've been uploading for you these Python notebooks. So this doesn't look abstract at all. Because this will be a way for you to look at how you can do these things in practice, right? So it's not just theory, it's how you do things in practice that I'm giving you support in this because I understand it might be difficult to understand how to do these things in practice. So, but again, can you clarify? An application of reinforcement learning from scratch would be useful for us also for the theory part. An application of reinforcement learning. Again, an application of reinforcement learning as an example or as an application in the sense that I'm going to start with the problem and I'm going to implement it for you from zero. Let me understand that, please. Anyway, continuing while you maybe reply to my question. Uh, Here on the MDP example, maybe this can help you understanding the situation. So let's say you have your robot, you have this room where we are in, you are at home, but we are in the class now. In this room, we have a very simple robot, and we want to let it navigate from this point to the point which is on the other corner of the room, okay? Now, I can create an abstraction, and I don't have to, right? I'm creating an abstraction now to create a small number of states, but I can also keep all the states that I can have as the continuous space, which will be from 0, 0 that I will set there to, I don't know, 10, 0, 10, 5, 0, 5. Okay? So these will be my coordinates. If I set the origin of my word in that angle, that would be my 0, 0. Then, I mean, this would be the metric distance until the end of the room. Okay? This can be all the states that I can fall in. So this is the set of states for me. Would be the set of states as all the combination of positions that I can get from 0 to 10 and from 0 to 5. Okay? I see other messages in the chat, but okay, so this is one possible set of states. Another possible set of states, which is the one that I'm using here, is I collect a bunch of positions in something that I call a cell, right? This cell of a grid. So I discretize my environment. I create some cells, and I say this whole part of the environment falls in the same cell. This other part of the environment falls in the same cell, and I don't care about the difference. Okay? This is just to abstract it. The actions available to the robot will be, of course, motor controls. Okay, so the controls that I give to the motors. Now, let me abstract this again. Abstracting means that I can predefine some controllers and say I have a controller for moving forward, controller for moving left, and controller for moving right, and controller for moving backward. So I'm creating a set of actions composed by 4 actions, which is move forward, move left, move right, move back. Now, the rest of the environment is defined by, of the Markov decision process, is defined, we said, set of states, actions, termination condition, reward, and transition function. Transition function is determined by the dynamics of the word itself. So if if the agent, the robot in this case, has some faulty motors, this will be just part of the word, right? So the way the robot moves, it's the transition function. So if I take an action from this state, what will be the state that I will be in? This depends just on the real world dynamics in this case, right? If I'm creating a simulator, it depends on the way I implement the dynamics of the simulator. The reward and determination in this case come from me because I'm creating an abstract problem in the sense that I'm saying this is my goal for the agent. So I set the reward to be plus 100 in that corner and minus 0.4 in every other state. This is what I'm deciding as the engineer that is creating this problem and formalizing it in the form of a Markov decision process. And similar for the termination function, I'm deciding that the termination function is in that state. So this is how you start thinking about an MDP when you have a certain problem. Of course, there will be termination states. So this is a simplification, right? Because there would be other termination states and other reward functions in this specific example, for example. If there would be another termination state when the battery of the motor, of the robot will die because it's out of charge. So that's a termination state. And that can have an associated reward that you can hand aside. But there is also an objective, for example, a reward function when the agent hits the wall. So if the robot is damaged, your reward function can be minus the cost of fixing the robot for the damage that it got. So there are some objective and some subjective reward functions. And again, this is up to you on how you want to formalize your problem. Of course, the formalization that you choose, in specifically for the rewards and determination function, but also for the abstraction in the states, will determine the way the robot will be able to learn. Okay? So this is how you start. And then you really just follow these algorithms that I've been describing. For the value function, for the value iteration algorithm, okay, let me say one more thing before going to that. So when I say I collect trajectories, what does it mean? I have my robot starting in that state over there, and the robot will take some actions until either it reaches the state over there, or I see that it's just going to hit a wall, or I see that it's never going to get there, so I decide to stop it, okay? So I say, if you don't reach that state after 100 actions, I'll decide that you will never be able to go there with this policy, so I want to reset you. What does it mean to reset the robot? I will take it physically from where it is and I'll put it again here. I will restart everything and the robot will start again its process. When the robot does this execution of actions, I'm generating a trajectory. Why? Because the robot is taking some actions, and these taking actions means that the robot is visiting some states. So these are part of my trajectory, right? Visiting states. I'm collecting the rewards. I look at my MDP and I say, okay, the robot is in this state. Okay, reward minus 0.4. And I sign it, I write it on my paper. And then I go to the next state, minus 0.4, minus 100, minus plus 100, whatever it is. Of course, I'm saying that I do it manually, but this is done internally, right, with the software that will be doing this and checking all of this information. Similar for the termination flag. Okay? So these are my trajectories, right? I have a bunch of states, a bunch of actions, and a corresponding rewards and termination flags for all of them. Then, by looking at this information, I can just really estimate a value function. And by estimating a value function, you can compute a policy. A policy can be, as we said last time, a greedy policy with respect to the value function, which means that I will be taking always the action that maximizes the value function. Right? So if I have to take an action, I look at my tables and I say, okay, what is the action that brings me to the highest value state? And this will be the action that I will take. So this is a greedy policy, okay? If I'm doing learning, I can be Epsilon-greedy, as I mentioned, meaning that sometimes I take a random action, and this is what actually allows me to change the policy of the agent, right? Because if the agent if the robot starts with a predefined value function where every value is set at 0, right? The agent will have no maximum action, so the agent will just take random actions, basically, or always the same action, the first one, and it will always stay, I don't know, let's say the random action that it takes is go right, or the first action is go right, it will stay over there for the whole time. Now, what happens? Instead of letting just follow the value function, I say, sometimes please take a random action, just sometimes. So by taking one random action here, it will eventually go over there, and if it keeps going right, it will follow all this corridor. So already there will be a major difference in the states that I've been visiting. And this can happen again, so the robot will be stuck in all this situation until it sees some positive signal which is over there. So you see, the robot needs to go over there, so there needs to be some exploration. So that's why you have an epsilon-greedy policy, or there are other exploration methods, as we have seen also for the bandit problems, but I mean, we'll get to those. Like, for example, I want to, I will give the agent a reward for visiting states that it has never visited. So these are called novelty-based explorations. So I want the agent to visit states where the agent has never been. So if the agent is being stuck over there, it would go over there because in this other new part of the corridor, and here and there, just because it has never been there. This is another method for exploring. Generally, all the examples in the theory part are based on epsilon-greedy, just because if you have a small epsilon probability of going random, if you take enough samples, or if you do this several times, you are guaranteed to cover all the possible states. So to start, this is an explanation, I guess. I have also another Python notebook that I will be uploading, where we are using a Monte Carlo method on the grid word. Again, on this grid word, the same that I have published in this MDP, will be computing a policy and the value for a certain policy. Okay. Okay, so how we differentiate between two trajectories if they have the same value of the value function? I mean, you don't need to necessarily. If they have the same value, it means that they will be equally good for the agent following this current policy, or so you don't have to differentiate between these two necessarily. If they have the same value, it means that they are equally good or bad. So in many cases, you will have values for states that are similar or exactly the same, and we don't care about this. Okay, so we can look at the example more in detail. Fast view of the code, sure. So let's try to move a bit forward here in the theory part, and we can look at the code after. Maybe, or if, let's do it before, okay? Because I think this might help clarifying how you can do things. Let's look at the code first, then we go to the Blackjack example, and then, I mean, whatever is the time that we have to go forward, we'll use it. But it's better if I don't lose you now, because it's it's when you are starting to think about reinforcement learning, you need to understand what's going on. So, okay, starting from here, we don't care about the imports. We have some imports over here. So I'm creating a structure here where this is just useful for me to collect my transitions, okay? Nothing else than an abstraction that is useful to formalize the problem. So the transition will be composed by a state, an action, an X state, a reward, and a termination. Okay? Then I create my grid word environment. So the grid word environment will be composed by a set of states, as we have said, a set of rewards, sorry, not a set of rewards, a reward function, a set of actions. There will be an initial state. I need to keep track of what is the current state, right? This is for the dynamics part of the word. I need to know what is the current state, the goal, and this is, I mean, the pits. This is in a Wumpus word like naming. Okay. Uh, and then the transition probabilities. Note that all this information is unknown to the agent in the reinforcement learning case, but in this example where we're looking at value iteration, will be known to the agent, okay? This is for value iteration, it's known. For every other, for reinforcement, because that's planning. For reinforcement learning, this information is unknown. So you don't know the transition probability, you don't know, I mean, the agent knows the actions, but it doesn't know the states, it doesn't know the rewards, okay? So I'm initializing my grid word by setting, I mean, the number of rows and columns that I want to have, the step cost, which is the minus 0.04 that I was mentioning before. So this, the cost that you have in every state that is not the goal state, okay? So I'm setting where my goal has to be and the pits. So where are the pits, okay? And also where are the obstacles. So in the pits, I will have a negative reward. In the obstacles, I will not be able to go because they are obstacles. And yeah, so I will create the set of states by just saying that it's an empty grid of rows and columns. Then I'm creating my obstacles if the user wants to have any. So I'm setting one in every state where an obstacle is. I'm creating my reward function basically here, which is, I'm creating my reward function in the form of a table where I'm mapping every state to a reward, okay? So as we said several times, a function can be a tabular function where we can just have a value for every possible state, and this is what I'm doing here. Or it can be a real function, okay? So here I'm creating the table. I'm creating the rewards for the pit states. And then this is just useful for me for looking at what's the action that the agent has taken. These are the actual actions. -1, 0 means going up. The 0, -1 means going left. The 1, 0 means going down. And 0, 1 means going right. So the initial state will be at the bottom left corner of the grid. And the current state to start is the initial state. I set my goal and I set my pits. And the transition probabilities, I decide them to be 0.8 for taking the true action that I've been selecting, and 0.1 for taking the left, the closest. So, for example, let's say the agent decides to go down. So the probability of actually going down will be 0.8. The probability of going left would be 0.1, and the probability of going right would be 0.1. Okay? And there would be 0 probability of going up in this case. Then I'm creating just a bunch of methods here which are just useful for me, where I'm just looking at what are the list of actions, what is the current state, what is the current reward, what is the current termination flag, where it's true only if we are the goal. Then it's a render function just to print give you a visualization of the environment of the MDP. And yeah, just this. And then there is my transition function, which is implementing what I've said before using the transition probabilities. Okay? Then what does it mean to take a step? I'm taking an action here in the form of the string, so I'm converting that to the actual real action. And then with a certain probability, I will actually execute the action. Sorry, here I'm using the transition probability. Here I'm just doing the deterministic version of it. Okay, so here I'm using the transition probabilities in the sense that I'm randomly choosing the actions based on the transition probabilities, because I've said that a certain action will result in the true action with this probability. So it's the same thing as sampling between the actions. Then I'm creating my transition, right? Because I'm saying the state is my previous state, which is the previous current state. I'm setting the new current state to the new state that comes from the transition. So this becomes our next state. The action is the action. The reward is the reward. Determination is determination. Okay. So now that we have this, we have also a reset function where I'm just setting again the agent in the initial state. So here I'm initializing a 3x4 grid word where the step cost is 0.4, the goal is in 0.3, and there is one pit in 1.3 and one obstacle in 1.1. So now I'm rendering it, you will see it. So this is my environment, bottom left state is where I start, this is the initial state, this is where the agent is, X is the agent. Here we have the goal, here we have one pit, here we have one obstacle. The current reward is minus 0.4 because we are in this state. The current state is 2.0, and termination is false, and the available actions are up, left, down, right. Now here I'm following for 5 steps a random policy just to show you what happens. So I'm choosing randomly between the actions, I'm printing the action that I'm taking, and I'm executing this action and rendering the environment for you 5 times just to show you that the environment is actually working as I've described. So I take action left, and the agent stays here because there is no left. So there is a wall, it stays in the same position. It went to left with the probability 0.8, so it actually got left. And it stayed there as a result. Then up, it's going up, down, it's going down, and the reward is minus 0.4 for each of these. Determination is false every time. Here it's going right, and again, this results in the wrong action because the dynamics of the word made it happen like this. So instead of going right, it went up. So that 0.1 probability took place, so gave us this outcome. And then down, it's going down. Now, I'm resetting my environment. I'm rendering for you to show you that it's actually reset. So the agent is again in the initial position. And then I start my value iteration. I initialize. So I'm creating a V function. A V function is a table. In this case, can be something else, but we decide to use a table. So it's a table of the same size. So where I want to map every state to a value, so I will have the same number of states that I have in my grid. Okay? So I set my discount factor to be 0.8, and this is the threshold over which I will stop my algorithm. So until convergence, so until when I don't reach this error to be the error between, when the V function is not changing anymore above this threshold, I will stop. So if the difference between the previous V and the current V is more than that threshold, I will stop. Otherwise, I will continue iterating. So here, this is just some useful thing to get the value, get V as a function. V of RC will be just looking at this. Delta is 0 to start. And then for every state, I'm looking at what is the reward, because again, now I'm looking at value iteration. So I know the reward function and I know the transition function, so I will use them. Normally, this is unknown to the agent in a reinforcement learning problem. This is a planning problem, so we know that. So I look at the rewards, all the rewards, right? And then for every action that I have, I look at the possible outcomes by looking at the transitions, right? Okay. So I look at the transition function, and then I do my um, um, expectation, my true expectation, basically, by summing the transition probabilities, by multiplying this by the value of that state. Okay, so I look at all of this, and then so I consider all the possible outcomes, I sum, and this is my expected value from that state, right? And then I'm basically checking whether the value is changed or not, is increased or not. If the value is increased, I update my maximum bit, and then I update my table as reward plus gamma times Vmax, which is the Bellman equation. This, if you don't understand this part, you need to look at the Bellman equation. Don't worry, it's just in the formulas. Then I compute my error as the difference between the new estimate and the previous estimate. If this error is more than a certain threshold, then I stop, otherwise I continue. And that's it. So this will be showing you the error that I get. So you see that it's converging. And so it converges, and these are the final values that I get. You see that the maximum value is over here in the goal state, because in all the other ones I get a minus 0.4 reward. And yeah, then if you try to maximize the value function, to take the actions, you will see that this will give you the best action to take. So this part is done. I hope it was useful. Let me know if it was not, because we'll try to change something. Okay. Now, Blackjack. Okay. So the goal of Blackjack is that of trying to get your cards that sum as much as possible, right? Close to 1, but without exceeding, 21, but without exceeding 21. So there are a bunch of rules over here that define the way the game is set. So all the cards where you have a face count as a 10, aces count either as a 1 or as an 11. Each player competes against the dealer, so it's playing basically just against the dealer. There is no other person involved. So one of the dealer's card is face up, the other one is face down. And if the player has 21 immediately, like for example an ace plus a 10 card, a face, it's called natural, and then with the natural the player wins only, wins always unless the dealer has a natural 2, where then in that case it's a draw. But if the player doesn't have a natural, it can request cards by one, so you can ask another card, another card, another card until you decide to stop. So the player can say, I stop, I don't want another card, or and then it checks the outcome against the dealer. Otherwise, it exceeds the 21. In that case, it loses. So if the player sticks, it's the dealer's turn, and we say that in our case, the dealer is following a fixed strategy, where it's sticking on any sum which is above or equal to 17, and otherwise it's getting another card. If the dealer exceeds 21, then the player wins, otherwise the one closer to 21 wins. So how can we formulate this in the form of an MDP? So of course, the dynamics is unknown because we don't control the cards, so it's unknown. So this is very clear. This is the dynamics of the world. The agent can only do some learning over here. Specifically, to be clear, in this example, we are looking at how to evaluate a policy. So we will consider a fixed policy. We are still casting the problem in the form of an NDP, but then we'll use Monte Carlo evaluation methods to see how good our policy is. Okay? So each game will be an episode for us, right? So, and the states are the sequence of cards that we get, right? So the actions that are available to the agent is sticking or hitting a new card, okay? And then you get a reward for only in the basically in the terminal state, which is +1 if you win, -1 if you lose, 0 for drawing. Otherwise, you have 0 reward, and there is no discount factor. So in this case, given that all the rewards are 0 except in the terminal state, the terminal reward is also our return, right? Because we are summing 0 plus 0 plus 0 plus 0 plus terminal state reward, which it will be +1, -1, or 0. So the terminal reward corresponds to our return in this case. Again, the actions are hit or stick. And the states depend on the player's card. So you have a bunch of combinations, of possible combinations that you can have, and also on the dealer's showing card. Why only on the dealer's showing card and not also on the cards that are hidden? Because we are in a Markov decision process and we want to keep full observability. So we're saying it's fully observable, only what we see. We don't know the other cards. We have another information in our state, which is whether there is a usable ace which is available. So whether there is an ace that the agent can use or the dealer can use. We also assume that there is an infinite deck so that we don't need to keep track of the cards. Okay? So we say the dealer has this fixed policy where it sticks on any sum which is greater or equal to 17 and hit otherwise, while we are now evaluating our own policy where we say that for our evaluation algorithms, the policy is fixed, and this fixed policy will correspond to the stick if the player's sum is 20 or 21 or hitting otherwise. Okay? So now the formulation of the problem is completed because I know the transition function actually is unknown. I mean, the reward function is unknown to the agent, but it's known to us in order to understand how the problem is set up. Again, this is unknown to the agent. The agent doesn't know the reward that it gets. Doesn't know also the termination, but we know us as engineers that are formulating the problem, we know what is the terminal state. And yeah, we know everything that we need to know. Okay, so we look at our policy by executing our policy for certain number of episodes. Now, specifically, we're looking at execution of 10,000 episodes and 500,000 episodes. What does it mean? It means that our agent has played 10,000 times this game, winning or losing or drawing. So it was reset 10,000 times. And the agent has been playing against the dealer for 10,000 times or 500 times. And by using this fixed policy, we collected our returns, so basically the terminal rewards, and we checked at how good our behavior was. So we basically saw that we can basically see that there is a lot of uncertainty in our estimate here because you see this from all of these oscillations that you have here. It's very uncertain. There is some variance over here. So after 10,000 episodes, we are not even able yet to evaluate how good our policy is. Why? Also because there is a significant component of stochasticity in our environment. So our environment is very stochastic. This is for the usable A's case. Because why? Because in the usable A's, I mean, this situation is less common. In the no usable case, sorry, no usable A's case, 10,000 episodes are fine. So sorry, I didn't describe what are the axes here. The axes are the card that the dealer is showing, and this is the player's sum. So these are the axes of our plot. So what is the value when the dealer is showing a card from ace to 10? And on this other axis, what are the values that we get on the player sum corresponding to each of these other values in the other axis? Okay? Instead, after 500,000 episodes, you see that the estimate is much more precise. Again, what I'm trying to show you here. I'm trying to show you how you can formalize a problem like Blackjack in the form of a Markov decision process. So we have seen that. And now we have said, let's say we have a fixed policy. How can we say how good this policy is? So this is the value of our policy based on this state that we can fall in. The value of our policy is the value of every state according to our fixed policy. If we change the policy, we can throw away all of this because our value will change. Okay? Let's see if there are questions on this. Do you have other questions on this? Please ask now. I can spend another couple of words on here. So, of course, in reinforcement learning, we don't want only to evaluate the value of a policy. We want to also find the policy that solves our problem. But in order to do this, we first need to compute how good our policy is. Okay, so this is a very important step to move forward in the direction of finding a better policy. We need to know how good this policy is in order to compare, to get a notion of better. In order to be better, you need to evaluate how good something is. And now we'll see how to do this as well. Now, yes, we have still some time. Okay, let's see if there are questions. Do you have any question? Is it clear or is nothing? I mean, it's completely unclear, and so you don't have questions because of that. Sorry? Okay. Okay. I mean, in a similar way, you can, maybe the simplest way that you can think of as a Markov decision process is a game, right? For example, if you consider chess, you can very easily formalize that in the form of MDP, right? So chess, the states will be all the possible combination of the states that you can get. The actions will be moving every piece that you can that you have in your board. The reward will be, I mean, you can cast the problem as you prefer. According to how you engineer it, you will get an according policy. But for example, you can get a very huge reward for winning the final game and a small penalty for, a big penalty for losing and a small penalty for losing every piece, for example, in your, every character in your chess game. And this could be one way of formalizing your problem, for example, in the form of a Markov decision process. And determination, of course, is only when you are at the actual terminal state of the chess game. So when somebody cannot take any more an action, then it means the other one has won. I don't see more questions coming, so I'm moving forward. Um, okay, so we said last time, we now have a way to compute V, but we don't want to use V, because in order to use V, we would need to know the transition function, right? Why would we need to know the transition function? Because if I know only the value of the next state, I still need to know how to get there. Which action leads me there? This is unknown because we don't know the transition function. So we don't want to use the V function, but we want to use the Q function. The Q function is the action value function, which estimates the expected return from that state by taking a certain action and following from therein the policy. Okay? So by looking at the Q function, we can then look at which action maximizes the value, the Q function itself, which determines for us a policy. So our policy evaluation then for Monte Carlo methods will be very similar to the one that we have just described, except that instead of estimating V, we will be estimating Q of pi of a state and an action. So, which would be an estimation of the expected return starting in a certain state S, taking an action A, and after that following a policy pi. So a policy pi is the policy that we already have. Okay? So in practice, this is different from estimating V because it allows us to compute a policy because we can do argmax of Q, which will give us, over the actions, will give us the best action to take. But essentially, it's the same as computing V. So similarly, we'll have the first visit computation for Q of SA, and then every visit computation for Q of SA. But now there are some complications in the fact that it is easier to visit states than to visit state action pairs. Why? Because there are some actions in some states that might be never visited. So this is a problem because we want to take, we want to look at samples of everything in order to compute correctly our estimate of the value function. So if we have a deterministic policy, which means that the probability of taking one action is 1 for a certain action and 0 everywhere else. So deterministic, it's a spike in one single action. You basically don't have probabilities. You only see one action for every state. And then this is a problem because your estimates never change. So it's exactly the example I was giving before. If you always take the same action, there is no way you can improve. And there are no ways to improve your estimates. So in this case, when the policy is deterministic, you can try to fix this problem by using what the so-called exploring starts. So you start your episode in a random state with a random action, and then you follow your policy, and then this allows you to compute. Basically, you have a non-zero probability for every state and every action to be the initial state and action. Okay. Okay. So what happens now? If we have a way to compute the value of our policy, so to do this evaluation step, right? Input policy, we evaluate our policy, we have our Q. Then we can also do an improvement step. This is similar to the policy iteration, similar to the dynamic programming that we have seen. So we compute a policy, we approximate a value for this policy. So we try to approximate as best as we can the value of this policy, and then we take an improvement step. And then this will create a moving target for us because we'll be estimating computing our policy, estimating our value of this policy, and then trying to improve our policy, and then changing again the value and trying to improve our policy, and so on and so forth. So we'll be alternating between steps of evaluation and steps of improvement. What does it mean? We start with any policy, can be, for example, a random policy, and we, by iterating between, alternating between evaluation and improvement, we will end up with an optimal policy and an optimal action value function. So it will be converging to the optimal ones slowly, and eventually it will converge. So the evaluation part is done exactly with the method that we have seen. So visit-based Monte Carlo estimate for Q. So you need many episodes in order to go evaluate your policy, and this way you will be able to compute an approximation of your action value function, which would be close to the true value of your policy. So we assume now that we are serving an infinite number of episodes, and we use exploring start. This is an assumption that we'll get rid of soon. But for now, assume that this is the case. So assume that we are serving an infinite amount of episodes, and we are using exploring starts. Then we also assume that in this case, if this is true, it means that we are visiting every state in action, and we are seeing so many episodes that we can compute the exact Q pi, the exact policy, the exact value of a policy for any policy pi. Okay? Now here we need to look at this theorem, which is one of the most important ones that we have in this course, and you need to understand this. What does it mean to take a policy improvement step? It means to make the policy greedy with respect to the current value function. And we'll see why this allows us to improve the policy by looking at this theorem. So if our policy is the argmax over the actions of QSA, then by setting the next policy to this greedy policy, we are taking a policy improvement. So let's look at this. So Q of pi k, right, in a certain state, so the value of a certain state and an action that is taken from the next policy, so the policy that is the argmax of the previous Q, is the same as the argmax of the Q pi itself. So here we're saying the value according to our previous estimate. So the values according to our previous estimate for the policy in a state, and an action that is computed in a greedy way according to the same Q estimate corresponds to the value according to always this estimate in the state and the argmax, right? Because we said this is the argmax of QSA. So it's the argmax of the previous estimate Q pi k in S and for every action. So if we take the argmax internally of the same thing, right? So we're taking the argmax of Q pi inside Q pi. This is the same as maximizing Q pi over A, right? So this is the same thing. But then this is greater or equal than the value that you could get by taking any other action, right? Because this is the argmax, so this is the action that maximizes the Q pi. So if we take the action that maximizes the Q pi, then we are taking the best action, so by taking any other action, we basically are not, sorry, we're not obtaining the same value that we would get by taking instead the maximum Q action. Which means that if the previous action was not corresponding to the argmax of this Q pi, so the previous policy might have been computed based on another policy, which was on another value function, sorry, which was on its own computed on another policy, which was on its own computed by another, based on another value function, then if it's not the same action, it's not the best action to take according to this value function, which means that is worse, which means that you can get the maximum value by taking an action according to the new policy, which is computed according to the argmax in this way, so to a greedy policy according to our value function. So this is a key step to understand. If you have questions here, please ask now. So if you have questions about this, please ask, because it's very important to understand. So this is based on the fact that you are improving your policy, and this improvement of your policy is leading you to an improved evaluation. So consider the fact, let's say, you start with a random policy, so the policy is completely random. Now we compute the value of our random policy, and if we take the best action according to this value, it will be certainly better than a random action, right? So this is the initial step. So we're taking a policy we're following a policy which is definitely better now than a random action, because it's computed based on some value. Now that we have a better policy, we can also compute a better value function, though. We can estimate a better value according to our policy. So if we have an improved value now, however, we can also, by taking the argmax of this value function, we also obtain a better policy compared to the previous one, and so on and so forth. This keeps happening until there is no more improvement, which means that you reach the optimal policy and the optimal value function, because there is no more improvement that can happen. Again, initial step is you start, let's say, with a random policy, you estimate the value of this random policy, you say, my new policy now will be greedy according to this value function, which means that I'll be taking the argmax of this value function, and this will be for sure better than by following a random action, right? This is clear. Now, if this is clear, it's also clear that by following this policy, I will obtain new episodes, new returns that will allow me to compute a better value function, because I will be able to estimate the value of a better policy. Right? So I'm estimating the value of a better policy, and this will be certainly better as well. And by looking at a better value function, I can improve my policy as well. And this is the key idea. I see no questions coming, so I'm assuming this is clear. If not, please ask before the end of this class. Repeat the theorem. Repeat the theorem. The theorem is the following. So if I have a value function which is computed according to any policy evaluation method, okay, and I compute my policy, new policy, as being greedy with respect to this value function that I have estimated, then I'm taking a policy improvement step, because my policy will be certainly better, or at most equal in value to the previous policy. This is the theorem. And this is formalized in here, and I have given you an example of when you start with a random policy. So if you start with a random policy, you compute the value of this random policy again. And this means that I'm now taking an argmax over something which is not random anymore. So this will be for sure better than behaving randomly. This is the first step. Now I will evaluate the behavior, the returns in expectation of a policy which is better than the previous one. So the value will be certainly better again. Now, if the value is better, though, I can also compute a better policy based on this value. And this keeps happening until convergence. Okay. So I said before, we made a bunch of assumptions, which was you take an infinite amount of episodes, you have an infinite amount of episodes, and every action is um, action and state is sampled according to the exploring start methods. So let's start by removing the infinite episode assumption. So of course, you don't have that. So you can take as many episodes as you want in order to obtain some error bound in your estimate. There are ways to compute that. And so you want to make sure that these bounds are, this error is below this bound that you set. Or otherwise, I mean, you can just assume that your policy evaluation is complete and you try to take a policy improvement step. The worst thing that can happen is that the policy stays the same, so you keep trying to estimate then your value function. Okay? So over many steps, this thing will get closer to the actual one. Now, this is the pseudocode of the way we can behave, or the way we can compute our policy and our value function using a Monte Carlo method. So this is the first full reinforcement learning algorithm that you are seeing on a complete reinforcement learning problem. Okay? So this is the first complete RL algorithm where you have an evaluation step and an improvement step. So the evaluation is done according to the same thing that we have seen before, where we are using, however, exploring starts because S0 and A0 are selected randomly in such a way that all pairs have probability greater than 0 to be selected. So we are starting from random initial state and actions. And then after that, we are following a policy pi. So we compute our returns as we did before. We're using first visit. So if the state and action do not appear in previous state and actions, then we improve our estimate. So we compute our return and we append it to our buffer of returns. Then we take that and we compute now the average of the returns for state and actions. Note that now this is returns for state and actions because we're using Q. Before we were estimating V, but now we're using Q. So we want to compute the returns for being in a certain state, taking a certain action, and then following a policy. This is why. And then we compute our policy by doing the argmax over A of QS A. Now we need to get rid of another assumption though. In a real world, in a realistic environment, in a more realistic environment, doing exploring starts is basically impossible, right? Because I can't select what is the initial state in many cases. It's not realistic. I mean, yeah, there are a bunch of slides before that. So we'll get rid of this assumption based on that. Let's look at the convergence first of this algorithm. So you are computing the returns for each A and S. We accumulate them independently of the policy. We will converge to an optimal policy in the end. So there is no formal proof of convergence for this algorithm, although there is no practical proof. There is no practical proof that it doesn't converge. So it's empirically proved to converge, let's say. So looking at the previous example of before, in this case, in Blackjack, we can start we can use exploring starts because we're using a simulated game. So we have our initial policy, which is the same as before, which is the same as before, and then we are using our reinforcement learning algorithm as described before in order to compute pi star and v star, where this means optimal policy and optimal value function. So We initialize our initial action value function at 0 for everything. And then by following this loop, where we do policy evaluation as we did before, and policy improvement by taking the argmax, and using exploring starts, we see that our optimal policy is the following when there is a usable ace, okay? And so um, if the dealer has this card and you have these other cards, basically if the player, the agent, has a card which is above 19, it will stick, otherwise it will hit, more or less, except when the dealer has between 2 and 8. And there is a usable ace. If there is no usable ace, then the policy will be more complex, so it will be hitting for any card between below 17 if the dealer has a card below 7, otherwise it will behave in another different way. So I hope this is clear how you can read this. And this is the optimal value function, which is the value of this policy, but also the true value or the true value or the optimal value that you can get from this Markov decision process. Now, I said exploring starts are unlikely in many scenarios. There are ways to ensure that you select an infinite amount of times a certain action. And these ways are using basically on-policy methods and off-policy methods. There are two ways to do this then, on-policy and off-policy methods. And I guess we'll see them more in detail next class. Maybe we can introduce on-policy methods, and off-policy methods will continue in next class. So for on-policy methods, it's very simple because we basically use a soft policy. So what is a soft policy? It's a policy where every action has a non-zero probability of being selected. Specifically, we consider an epsilon-greedy policy. And in this epsilon-greedy policy, all non-greedy actions are given a minimum probability of selection, which is epsilon, or actually epsilon divided by the number of the actions. And the greedy action instead has probability 1 minus epsilon overall. So the epsilon soft probability action, policy, or epsilon greedy policy, is the one that we already introduced in the case of the bandit problems. And it's a policy where we take every action with probability epsilon, and with probability 1 minus epsilon, we take the greedy action, which is the action that corresponds to the argmax. Okay? How do we change our algorithm? Just in the following way. We compute still the argmax to compute what is the A star, the optimal action. But then we update our policy as follows. For the optimal action, we assign probability 1 minus epsilon. And for the non-optimal action, we assign basically all the other actions. We assign an epsilon probability. And that's it for this part of I mean, here there is some proof that the policy improvement theorem still holds. We don't need to go through this. The theory is the same as before. It's just that you now are guaranteeing that there is that every action is being sampled sometime in every state. So the more number of episodes, the larger number of episodes, the larger the number of samples that you have, so the better will be your improvement and your evaluation. So in this way, you are guaranteeing that you are exploring enough. Again, this epsilon greedy part is done only when you are learning. Once you finish learning because you see that you converge to the optimal value function, to the optimal policy, you will just do the argmax. You will just be greedy. You don't want to be epsilon-greedy anymore. You don't need to explore anymore. Exploration is only for learning. When you need to use your policy, you just use that. So let's see if there is. Can it happen to have some case of divergence? So the answer is no, if you do things properly. In the sense, if you collect enough trajectories, you will not diverge. If you don't have enough data, it might happen. That's the answer. So you need to do enough sampling, basically. So Monte Carlo methods, as we said, are methods where we sample returns, and based on the sampled returns, we do our estimates. As you can imagine, given that we are sampling trajectories, you can have a large variance, right? So you can have a lot of oscillations, and it's hard to estimate them without having a lot of data, because there is a lot of variance in estimating long trajectories, right? Trying to compute the returns of long trajectories can be problematic. We'll see methods that will reduce this problem for us. And we'll focus on off-policy methods next time, and we'll see also, we'll move forward with moving with the other methods. So yeah, that's it for today, and yeah, see you next week.